have also seen this diagram before, and we see that most of the lignin is actually in the secondary cell wall. So it's actually part of the cell wall, although the middle lamella contains about 70 to 80% lignin. So there's very few other components in the middle lamella, and it is this layer that we need to remove. So as we penetrate the liquor through the cell wall to get to the middle lamella, obviously the lignin in the cell wall will dissolve before the lignin in the middle lamella, and this means that we will change the structure of the cell walls, and we can also see that the hemicellulose is mainly removed during this first impregnation and the initial cooking phase. And then, as I said, that the middle lamella needs to be dissolved for the fibers to actually separate. Okay, so back to this graph and the different phases. Okay, so what happens during each of these phases in terms of the reaction with the lignin? So we can see during the impregnation phase there's very little lignin dissolved because our temperatures is below 140 degrees Celsius. And then during the bulk cooking phase, when the temperature has risen to 140 degrees Celsius or higher, we have this dramatic increase in the delignification rate. For every 10 degrees Celsius, just remember that the rule of thumb is that reactions double when the temperature increases 10 degrees Celsius, but actually for lignin reactions it more than doubles. And this bulk cooking reactions depends now on the OH and the HS. Okay, and it also depends on the rate of diffusion of the liquor, and that is now the diffusion of the liquor into the fiber cell walls and to the point where they have to react with the lignin. And also, obviously, after we've now reacted with the lignin, that lignin has to dissolve into the liquor, and that is also a rate limited step. Okay, so by the end of our cook and the bulk cooking phase, we have about 70 to 80% of the lignin that has dissolved, and then in the last residual cooking phase we remove about another 10% of lignin, so that by the end of the cook we have removed something like 90% of the lignin, not all the lignin. And after this the reaction rate slows down, and at this stage we do not want to cook more, because now the lignin is not there and the cellulose is exposed, so that can now react with our chemicals. And lastly, we also need to make sure that we do not use all the alkali. So you can see in the graph not all the alkali has been used by the residual phase, and that is because we want the residual to prevent lignin from recondensating and going sit on the pulp again, so the lignin that has dissolved can repolymerize, and unfortunately it does it onto the fibers. And obviously we do not want that, because then basically we have just moved the lignin from inside the cell wall between the cells to on the surface of the cell walls. Okay, so lignin is depolymerized by mainly the SH ion, and water-soluble fragments, so-called sodium phenolates, are formed. As we've mentioned already, we can get recondensation reactions or repolymerization, and these will form dark insoluble products, and if they sit on the fibers, then they actually become problems for later bleaching. And then lastly, just remember, we have seen this graph also before, that the removal of lignin will depend on the percentage of lignin in the wood, the type of lignin, and there we have discussed last year in your module about the chemistry of lignin, something called the SG ratio that can have an effect, and obviously where precisely the lignin is in the fibers, between the fibers in the cell walls. Okay, although the aim of our cooking is the removal of the lignin, we have now mentioned a few times that the chemicals will react also with hemicellulose and cellulose, and the ratio is more with lignin than with hemicellulose, and in the least with cellulose, but it will react with hemicelluloses, okay, and cellulose. So the reaction that can happen is the deacetylation of hemicellulose change. We have not really discussed this, but hemicellulose has these acetyl groups that can be removed. The peeling of end units, that last glucose or xylose in the backbones of either hemicellulose and cellulose can be removed. Fortunately, there's also so-called stopping reactions, and these reactions basically form stable end units. The next one is the formation of hexauronic acids, and this comes from the hemicellulose, and hexauronic acids can lead to brightness reversion of our final paper products. The next one is that the alkali can react with the glycosidic bonds in a cellulose polymer chain in the middle somewhere, and that will break the chain into two, so you have shorter cellulose polymers, and as we've seen, that means that the pulp viscosity will be lower. Some of the xylane that comes from the hemicellulose can, if it goes into solution, if the conditions is right, can actually reabsorb onto our fibers. So we have already mentioned that hemicellulose is mainly degraded during the initial delignification phase, and during the bulk cooking phase not much hemicellulose is removed, but in the end, when all the lignin has been removed, in the residual phase you can actually have an increase in hemicellulose degradation and even cellulose degradation. The other reaction that we find is that acid groups are generated during this reaction with our carbohydrates, and this unfortunately means that we have that will react with our alkali and consume alkali, and then, as we said, the cellulose degrades to a lesser extent, mainly during the residual phase. Okay, and this will unfortunately mean that by alkaline hydrolysis and chain breaking, that the viscosity will be lower and therefore the strength will be lost.